as we just start the intros and stuff. But yeah.
hmm Okay. Um, Sorry, I was having some video issues. Hello, everybody. Thank you for joining. Today, we are going to be answering all of your questions around explanations and chain of thought in an LLM as a judge. This is the second episode of our series on Evals best practices, and we're very excited to bring you more good stuff. So, in today's talk, we're going to be answering all of your questions around like, why do we ask LLM as a judge to produce explanations? Does the order matter? Uh, what's the difference between chain of thought and explanations? And then what the heck do we do about reasoning models? So there's a lot of research that's been done in this area. We hope to review all of it with you. My name's Elizabeth, and I'm an AI engineer at Arise on the Phoenix open source team. And I am joined by Sri. You want to introduce yourself?
Yeah. Hey guys, my name is Sri. I'm an AI engineer on the DevRel team here at Arise. So do a couple different things, but both of us kind of have a main focus on evals and some of this like evals best practices stuff. So if this is your first time here, you'll probably see us a lot more in the upcoming weeks every time we do one of these, essentially. But yeah, we can go ahead and get started. Um,
Oh, yeah, I need to share my screen.
awesome.
All right. So you may have noticed that for all of the LLM evals, we produce an explanation by default. And we're not the only library that does this. This is now a well established best practice. And we wanted to review the literature on why we do this and kind of dive deep into it. So here are some screenshots of the new evals library. If you hadn't heard, we just released Phoenix Evals 2.0, which is a brand new Python library for doing AI evals, and we're really excited about it. You should definitely try it out. But in the evals library, all of our LLM evaluators return an explanation by default, and it is returned as part of the score. We're really treating it like a first class citizen. And while you can turn off the explanations, we generally don't recommend it because we firmly believe that the explanation is not only going to improve the quality of your evals, there's evidence to suggest that it improves alignment with humans. But we also think that explanations are a useful artifact in and of themselves.
Yeah. So that's kind of the main point, I think, to start us off of one of the biggest takeaways is that evals or explanations rather in evals really are their own artifact. And so I think the point here is that LLM-based evaluators are pretty different from older metrics. Like if you were just to calculate accuracy, for example, those older ones are kind of deterministic, right? Like you either match or you don't. But LLM-based metrics are a little bit more subjective. So that's like the entire power behind why we even want to use and harness those metrics that are LLM-based. So you can capture things like coherence, persuasion, like fluency, whatever, right? But the flip side to that is that it in general needs a little bit more tuning and oversight to kind of stay reliable. And so I think that's where the explanation part of it comes in. So whenever the model doesn't just give you, like, if the model can give you a score, but it can also tell you why, and then you have something that's actually useful to use. So something that I notice a lot is when I'm running my own experiments and I'm getting, I don't know, 50% um, hallucination, for example, right? Like that's helpful to a certain degree, but I think understanding why the models come to that conclusion of labeling them to be hallucinated or not, as an example, is like extremely helpful. And so there's kind of two big ways that we kind of see these explanations helping. So first is with kind of tuning your judges. So looking at the reasoning shows you not just the outcome, but kind of the process behind it. And so you can catch things like biases or inconsistencies or just places like where the rubric itself is being misinterpreted or when your application needs to start shifting. And then the second, I think, is mining feedback. So if you collect these explanations across like a whole bunch of examples, you get that whole layer of like the qualitative signal. So it's way richer than to just see your number of whatever your labels and score move up and down. So you can see patterns. You can see if it's, I don't know, like if there's long answers that's being penalized or if it's favoring a certain type of response. It just gives you a lot more insight into exactly what's happening. And so the key point here, I think, that we're getting at is that I think the explanations aren't just a nice to have, but they're like a real valuable asset that you can then analyze, repurpose, and then kind of build on to make your evaluators and your models better and in turn help your application.
Yeah, so what does the research actually say about this? There's now robust evidence to suggest that asking an LLM to explain its reasoning will improve the quality of its responses on a wide variety of tasks, so not just in the context of evals. And intuitively, this makes sense, right? Like the explanation provides a place for the LLM to kind of think out loud. It's like using a piece of scratch paper to work through a problem, right? Even I need that sometimes. And because the LLMs, the generative models, the explanations give them a place to ground that reasoning. The explanations have also been shown to reduce variance in the final responses when repeated multiple times. So this can contribute to increased consistency and stability in your scores over time, which is often desirable. So then I had this question like, okay, we want to produce explanations. We know that that improves results, but does it matter? Does the order matter? Does it matter if you produce the explanation first and then the score, or the score and then the explanation? There's only one paper I know of that has systematically compared these two prompting conditions, and the results were pretty surprising. I kind of expected that producing the explanation first and then the score would be significantly better than the other way around. But interestingly enough, in this paper, they compared like several different LLM-as-a-Judge prompting conditions. Two of them were this rate explain, where the explanation was produced after the score, and then analyze rate, which was write your explanation and then produce the score. And they actually found no statistically significant difference between these two prompting conditions, indicating that order doesn't matter. And that's really interesting, right? There's not a significant difference, but there is a small positive effect of producing explanations before the score. So that's generally what we recommend. And since this hasn't been sort of more widely studied, I think it's safe to assume that producing the explanations first will be as good, if not better, than the other way around. And so under the hood, all of our evals do this naturally, even when we're using tool-based LLM calls and structured output, we always produce the explanation before the score. So then we have explanations. What about chain of thought, right? Chain of thought is kind of like producing an explanation, if you think about it. Before I get into the research on chain of thought in evals, I wanted to do a little bit of history so you have context around what even is chain of thought, where does it come from, what does it mean? I think there's still, people have different definitions of it, right? So the term chain of thought as a prompting strategy was first introduced by Google Research in 2022. And in that paper, they showed that adding the intermediate reasoning steps to few shot examples in a prompt improved the results on a number of benchmarks. So instead of just putting the input and output in your few shot examples, you add the intermediate reasoning. And this work was actually inspired by the observations that asking LLMs to produce explanations improves results because they kind of intuitively notice that having the LLM think out loud in some way grounds its final response in sort of logic. Um, so that was a really meaningful paper. Shortly after that, we got the zero shot version of chain of thought. So while this initial chain of thought prompting was a few shot prompting strategy where you provide examples, we then got a zero shot version of that, which is the let's think step by step paper, which basically showed that just by adding a single sentence, let's think step by step, to the end of your prompt, you can improve results compared to not having that one sentence in your prompt. And this is kind of widely used today because obviously it's super easy to just add that one sentence to the end of your prompt. Importantly, though, it did not achieve the same great results as the few shot chain of thought prompting strategy, which takes a little bit more time to craft those examples and add the reasoning steps. But yeah, so that's a little bit about the history of chain of thought in general. The history of chain of thought in evals specifically, the sort of most prominent example of chain of thought prompting used in an evals context comes from the G-eval paper from Microsoft Research. This was one of the first LLM-as-a-Judge paradigms and was really, really significant and influential. People are still using G-eval today for a number of evaluations. And the core contribution here is that they suggested combining some human written evaluation criteria with some LLM generated evaluation steps. So this they call the auto chain of thought. And then that is your final prompt that you use for running your evaluations. And this is obviously really easy because all you have to do is define the criteria and then use the LLM in a sort of meta prompting style to generate the evaluation steps for you. And like I said, this is still widely used today. I do have a little bit of beef with this paper, though. There's several issues with it, but the biggest gap in my mind is the fact that they don't compare G-eval to any other LLM-as-a-Judge style metrics. They only compare G-eval to the sort of outdated heuristic metrics like blue and rouge, which of course are not going to perform as well compared to human judgments as any LLM-based evaluation metric. I really wish that the authors of this paper had included a more comparable baseline that used an LLM, even if it was just a simple prompting strategy. So yeah, there's all this fancy stuff that G-eval does, but they don't actually show how much the chain of thought prompting pattern contributes to the results that they're getting. And actually, subsequent studies have shown more mixed evidence on the role of chain of thought prompting. Most show that there is little to no benefit. So yeah, we don't really have enough evidence to say that chain of thought style prompting in the evals is going to improve your results significantly.
Yeah, and I think just kind of adding on to that, I wanted to show two examples specifically that kind of highlight why the impact of chain of thought in evaluations is pretty mixed. So on the left there, yes, the left there, in like a medical question answering space, it's a study in the medical question answering space. They essentially tested different chain of thought prompting strategies. So things like traditional chain of thought, React, I can't read what's on there, React, chain of thought, self-consistency, and even interactive chain of thought, and essentially compared them against like a really simple baseline. And what stood out is that the baseline actually did just as well, or in some cases even better. And so that kind of just suggests that adding chain of thought phrasing isn't enough. So without having like clear, well-structured instructions, you don't necessarily just get better results. And so on the right there, though, we see a very different picture in the math reasoning aspect of it. Going back to like the image from a couple slides ago. So here, like the zero shot chain of thought gave some gains, but when combined with like more structuring prompt like plan and solve, so essentially the more few shot type prompting, the performance really jumped across multiple data sets. So the improvement seems to come as much from like carefully written, detailed instructions from chain of thought itself. And so I think the bigger takeaway here is that you can't just assume that chain of thought will automatically be an upgrade. Sure, I think like the idea of it's a little bit more complex. Well, complex doesn't always necessarily mean your results are going to be better. So I think it really just depends on the task. And oftentimes I think that the real lever is just your prompt clarity. And so for evaluations that kind of require that multi-step reasoning, go back, check your answer, kind of almost like mental math is it's accurate, but it's a little bit easier to actually verify that your answers are correct when you're showing every single one of your steps. Kind of like that's the way to think about it. I think chain of thought can really help. And so for simpler, more qualitative judgments, I think it's just expensive, complex, and we'll talk about that a little bit more when we talk about reasoning models as well. But it kind of has all of those added things without really giving that much back, I think is what we're getting at.
Yeah, totally. I kind of think that any benefit people are seeing with the chain of thought style prompting is just an artifact of writing better prompts. And the better, like, you're going to get better results if you can really clearly define your evaluation criteria. And that's going to get you way further than simply adding, like, let's think step by step or something really generic like that.
Yeah, totally. It's just so interesting to see.
Okay, so then now what about reasoning models? How do they fit into all of this? We now have these reasoning optimized models that are like OpenAI's O series, O1, O3, and DeepSeek's R1, which are just crushing all of the benchmarks, right? They're sort of state of the art. But what are those about? And these are basically just LLMs that talk to themselves, right? They're internally doing a chain of thought process that is just hidden to the user. And but the difference is that they're specifically trained on high quality reasoning traces. So you're generally going to get better results than if you just prompted a normal LLM in a chain of thought style because it's baked into the training. Um, so the way that these reasoning models work is they spend some time talking to themselves before responding. And so while they take a little longer to respond and use more tokens, they're generally better at complex reasoning tasks like multi-hop question answering, code generation, structured problem solving, things like this. And we don't have as many benchmarks on how reasoning models perform in an evaluation context specifically, but we do know that they excel generally across these complex reasoning benchmarks.
Yeah. And so I think logically and conceptually we kind of felt like this, but I think we also wanted to kind of put it for the test ourselves. And so we wanted to see for ourselves like are reasoning models actually worth it when using them as evaluators? Like what model should you use as your judge model, right? And so here's what we did. We essentially ran a small experiment comparing a reasoning model and a non-reasoning model. I think does it say there O3 and I think GPT-4 was what we compared. Um, on basically the exact same evaluation task. The task was generally about evaluating if an agent had called the right tool or not, so kind of the router part of the agent. And then we created these two evals, essentially evaluating the exact same thing. One was a little bit more complex with the options for like essentially what to label. I think that we added like three options, like a partially correct situation. And then the simple one was just like a a one in one. And so we ran these through reasoning and non-reasoning model judges. And so on the top there, you can see the results for a simple evaluation. So essentially, both models agreed on all of the samples. So if they were both wrong, they were both wrong. And if they were both right, they were both right. And so the judgments were literally identical. But then we can like look at the cost there. And the non-reasoning model used about 7,000 tokens, and then the reasoning model used 21,000 tokens, almost 3 times as expensive just to get the same result. So I think that kind of goes to show of like, here's an example of like a task that is simple, like it's not worth it to use your reasoning model. And then on the bottom, that's when we kind of pushed it a little bit harder with the more complex evaluation. And so this time, the models did disagree on one sample. And I think like obviously because it's not deterministic, like every time I ran this, I would get like slightly different answers, like all samples, one sample, two samples, but it was all fairly low. It's not like they were disagreeing on like half of the data set or anything like that. But again, if it was like more than that, I think then it goes like, okay, we can physically go into the data and see like which model we necessarily agree with. And then that would be a separate aspect of it. But considering that they were pretty similar in their results, once again, like the reasoning model still used more than twice as many tokens as the non-reasoning model. And I think it was for one sample or a really low number like that. Um, I think the takeaway is like pretty clear. Just like for most evaluation tasks, I think that the reasoning models just don't give you that meaningful boost in quality. We think that the reasoning models are like so complex, like they're so good. But in general, I think they just add like significant overhead and latency and cost. So I think there might be best reserved for evaluations that kind of really require complex multi-step reasoning. And actually, it's interesting because we ran another test that I don't want to say too much because we might do another one of these on it, but for like our binary and score eval situations, like that was really complex. It was like, okay, like the evaluation there was like you have 1 through 10, like pick any number 1 through 10. Like there is infinite numbers, right? And so I think we did see in that case that the reasoning models were a little bit better. But again, like you're still paying a premium, at least in this situation, for the exact same answer. I think is kind of the idea here, especially the results of our test. And I think there's a notebook of it that I can put in the chat if anyone wants to run it for themselves. Um, but yeah, that was kind of what we had found too. Oh, there it is. Awesome. That was it for this one. Okay, and yeah, and then here we are with our takeaways. I'll start us off. Let's just land with the takeaway. So I think that the idea here is if you're building with LLM evaluators, I think there is a couple of different things to think about, right? Like for subjective or qualitative tasks, things like more creativity, humanness, fluency, whatever, I don't think that you will need fancy reasoning models. I think a standard model with explanations turned on will kind of give you the best mix of like alignment and transparency. I think the idea there is if the model is told to explain itself, I feel like I'm not gonna say it's like gonna correct itself, but I think it kind of does a little bit better because it's like, okay, I actually have to like think about it. I can't just throw out like yes or no or whatever. And then I think when we move on to like complex multi-step reasoning tasks, so things like multi-hop QA, dependency checks, structured problem solving, I think this is a potential where those reasoning models can actually pay off. But even then, I think making sure that you're also capturing the explanations because those traces are what will let you actually debug and improve over time. And then the last kind of group of tasks I think is for the well-defined task with a ground truth. So think like a correctness check or a reference comparison or something like that. You probably won't need chain of thought or reasoning models at all. I think a basic model is enough. And if you want, you should still collect those explanations, not necessarily to improve accuracy as much, but just to have artifacts that you can kind of use later on. So I think our big picture that we're saying is that reasoning models aren't just the default answer. Um, I think that they're a tool to pull out selectively when your task really calls for it. And obviously, latency and cost is something to always keep in mind. But regardless of all this, explanations are the universal piece, right? So whatever models you're using, they give you the stability, visibility, reusable feedback. I can go on, that you can actually like act on and like do something about. So if you remember nothing else from this, just remember to use explanations everywhere, honestly, I think. And only really pay the extra cost for reasoning models when you know you're going to benefit from the extra added reasoning power, is I think what I have to say. Elizabeth, do you have anything to add on there?
Yeah, I guess what we're trying to say is I generally recommend that keep your evals as simple as possible. These are sort of these are things you want to run quickly at scale. Um, they're providing you a signal. The same sort of best practices apply here as anywhere else in machine learning and data science, which is you want to look at your data and make sure that your evals are doing what you expect. And you should be doing this regardless of the prompting strategy that you use. And the only way you'll really know if you need a more quote unquote powerful prompting strategy or a more powerful model is if you start with the simple thing and see maybe there are gaps in its capabilities for your specific evaluation task. So this is our kind of recommendation. You know, all of the evals are a balance between the task complexity, the quality or like human alignment you're looking for, and then the latency and cost introduced by a given model or prompt. So that is all we had for you today. I did see there's some questions, so let me take a look at those. We got a question about evals 2.0. Seems to be a lot of focus on chain of thought. Have you all done any work comparing other patterns like React or tree of thought? We haven't looked into those specifically. There's nothing that would stop you from using those kinds of prompting patterns with the evals library, though. We keep it very flexible so you can kind of invoke the LLM in any way that you want. And yeah, I kind of have low expectations about these kind of fancy prompting strategies in general. I think just writing a good natural language prompt where you're very explicit with your criteria is going to get you further than any kind of generic prompting strategy. If you've ever tried to write guides for human annotators, I would use that kind of level of detail. Like talk to the LLM the way you would talk to a human and provide examples, provide as much detail as you need. If you've ever worked with human annotators, you know that they need a lot of help with understanding these tasks, which may seem obvious to you, but are not at all obvious once you actually sit down and try to label examples using some basic criteria. So being as explicit as possible will get you a long way. All right, next question. Were the prompts used significantly different for both models? Also, reasoning models aren't very deterministic because we can't set temperature equal to 0. Shri, do you want to take that one?
Yeah. Okay, so I think the prompts that we used in our experiment were essentially the same for both the reasoning and non-reasoning models. Um, I think the difference isn't necessarily in how you phrase the instructions themselves. Like the reasoning models themselves are trained to do like their internal kind of hidden chain of thought, whether you really ask for it or not, right? So I think the comparison was pretty fair, same task, same instructions, like just just different internal like behavior and cost. And then I think so that was like the first part. And then the second part on reasoning models aren't very deterministic because we can, yeah, so I think that reasoning models tend to be a little bit less deterministic, right? Even if you try to lock things down with temperature. I I think that's just because of the way that they expand and isn't it with the way that they like prune their hidden reasoning steps? So